my statics friends. In the last couple of videos we've been talking about equilibrium, and we showed you how to do it with scalars, we showed you how to do it with vectors, particles, three-dimensional space. It didn't matter. Now we're going to work some examples and hopefully drive it home. So without further ado, let's get it started. So just to recap, in our previous videos we've been applying the equations of equilibrium to an object, and so we've got a little bit of information just to kind of remember. We're going to be drawing free body diagrams. We're going to follow our WISE methodology. WISE meaning that it's self-weight, and I know these aren't in order. Self-weight, internal, supports, and external. WISE, W-I-S-E. We've got that. We know that we need equations of equilibrium, whether it's 2D or 3D, it doesn't matter. We're going to do the sum of the force vectors equal to 0, the sum of the moment vectors equal to 0. Done. Okay. For 2D, we can break these down into scalar equations, and we get the familiar sum of forces x equals 0, sum of forces y equals 0, sum of moments equals 0 for the scalar quantities if I choose to do it in 2D. And if I choose to do it with scalars or 3D, I get forces x, forces y, forces z. The sum of all of those equals 0. Okay, and then the sum of the moments about x, sum of the moments about y, and sum of the moments about z all equals 0. Okay, our sign convention that we're looking at for moments, again, if we apply a right hand rule and kind of do the twist around the x-axis, hands going in the direction of the arrow, thumb is pointing to a positive x, that's a positive moment. About the y, I'm doing this, thumb is pointing up, that's a positive y, and then likewise the z, I get my hand under here, is doing that, z is in the positive, okay? And of course the forces in the x are always pointing toward their positive counterparts, and that's the way we're going to set this up. All right. So before we get into some of the actual examples, let me show you a couple of problems that can appear that can make what we call as an improper constraints. Okay, a type of problem, and they're pretty obvious, but sometimes you get scenarios where you can't detect them, or you don't notice them, and the equations will prove this out for you. You'll be able to tell if an object is in equilibrium. So for example, let's take a bar that is supported by 2 pins. Okay, and then relative to this, if I go in and I have an arm on this bar that sticks out a little bit, say 0.6 meters, and I put a 400 Newton force, okay, we can look at this and, and say, okay, well, that's a pins, ball and socket, 3D pin, no problem. This is a pin, ball and socket, 3D pin, no problem, and then I got my applied force. We could run our Y's on this picture. And the free body diagram would look something like the following, okay? And so if I have a x, a y, and a z, that's my ball and socket for A. And then I get bx, by, and bz as my ball and socket for B. And again, I've kind of chosen my coordinate system such that x is down the length of the bar, y would be over this way. And then if we do a right-hand rule on that, that would make z positive upward. Again, you got to kind of watch the coordinate axes, but that's our general sign convention on this. Okay, and then I get my, so there is no mention of self-weight, that's not in there. We didn't cut anything, there are no internals. Okay, our supports, we did those are the ball and sockets, and then we have our external load, which is this 400 Newton force at a distance of 0.6 meters out on this arm. Okay, now if we take a look at this, what happens is if I take in some moment, say about A of this, okay, what will happen is that we will get an instability in the moment about the x-axis. And part of the reason is that we look at, by some moments, ax, ay, and az are all on the x-axis. And in this one, bx, by, and bz are all on the same axis. Okay, and then we go in and this force here, the only force that's not on the x-axis is this 400 Newton guy. And if that distance is not 0, this guy is unstable in the moment about x, because the whole equation for the moments about the x-axis, if we do this, is basically going to be 400 newtons times 0.6 meters, okay, and that's the only term. And does that equal 0? And the answer is no, it doesn't. It can't. Okay, so we would need something else to help stabilize this. This bar would just kind of flip and it would rotate on its own as well. So it is not in equilibrium with that force on it. Okay, but again, the equations will prove all of that out for you. But that's something to look for if you have a bunch of all reactions that are acting through the same point or same axis. Okay, again, the reactions, not the applied forces, now you've got a problem. Okay, because there's no value of my unknown support reactions that can make this be in equilibrium. Okay, all right, so that's the first one. Okay, the second one is dealing with, again, more instabilities of the supports. And now I have an object, and this is a real common physics experiment to kind of locate centers of rotation and stuff. You may have done this in a physics lab. I remember doing this one. But we had a kind of a weird rounded object on here, and then it was pinned. It's pinned at A, pinned at B, pinned at C, but it had these two linkages that were on here. And so it's pinned here and pinned here. This is called a two-force member. Okay, and one of the things about it is that the force that is in the member is directed along the line of action of the member. Okay, if you have a series of these linkages such that the line of action of the linkages all meet at a common point, and then I come apply a force somewhere that's not at that point, this object is no longer in equilibrium. Okay, and that's, again, because the force in the linkage acts along the line. So if we draw our free body diagram, this is the valid free body diagram for this picture. If I do sum of moments about that point O in the middle, this is a 0, this is a 0, and this is a 0 moment. The only thing that's left is 100 times 0.2. And again, it's the same problem that we had before. So this concentric or concurrent forces is a big issue. Okay, so the sum of the moments is not equal to 0. All reaction forces are concurrent through the same point. Okay, that will cause an instability as well. In order for an object to be stable, I have to have multiple lines of action of support conditions to help us out. Okay, the next one that we have is kind of the same object, but instead of being concurrent through the same point, now if I draw this, they're all parallel. Okay, and this is called a parallel force system. And so if I have a parallel force system, unless this force is applied in the same direction as that line, in this case it's horizontal, what happens is that if I look at the equation, free body diagram, here's FA, FB, FC, those are the linkages. Okay, and so what will happen is that 100 newtons has nothing to balance it. Okay, so sum of forces in the x is equal to 0 on that one. So that's kind of what we're looking at. If we go in and we now start to kind of think about this, in statics we assumed everything was rigid and there was no deformation that was allowed. Okay, but when we get to mechanics and materials, what you'll find out is that this object will deform, and it doesn't take much to put something back into equilibrium. All we have to do is apply this, and if this thing moves over a little bit, say to like that, this force would also move over, and now if it's linked up here, we've now inclined that linkage just a little bit. It went from here, and if I exaggerate it, when I pull this bar over and I let it deflect, it now is oriented that way. When it deflects like that, now it's got an X component associated with that, and that would be the same for all of these. So, a perfectly parallel system will be unstable for any load that's put on it, but it may get to a point where it can resist the load in a very quickly based on a very, very small displacement. So it doesn't take much to put this guy back in equilibrium, but on his own, he is unstable. You could move any weight object, this could be 2 trillion pounds of force. I could move it left and right as long as I get those forces parallel to each other. Okay, and that's kind of one of the tricks. Now there are other things obviously for moving 1 trillion pounds we don't want to deal with, but that's the idea. So keep your eyes open for these commonalities, these concurrent points, or these concurrent axes, or even the parallel force system, and know that these are unstable. Now, if you don't know it, you can always go back and do the equations and do the statics and prove it. But these are some of the tricks, now that you know the basics of the equations, some of the tricks that you can look for to identify a particular problem. Okay? All right, so those are real good kind of definition type questions that might show up on a test if you're one of my students. Hint, hint. Find out who's watching this video, right? Okay, all right. So let's take a look at some actual real examples for like equilibrium in 3D. Okay, the first one, I've got 2 examples for us. One we're going to do with vectors. It'll be similar to what we did in the last video. But we've also got one that's in 3-dimension that we're going to try to solve this guy in scalar form. Okay, and again, usually what equilibrium involves is finding unknowns. Like maybe I want the tension in the cable, or I want the values of the reaction at the ceiling, or the value of the reactions at this roller, whatever the case may be. That's generally what we're after. So in this example, we're going to be looking to find that we know that we have a mass of the plate is 100 kilograms, meaning that the weight is 981 newtons. And again, we're going to take that, multiply that by 9.81 meters per second squared. That gets me the 981 newtons on that. Okay, the reaction, what we want to find is we want to find the reactions, the unknown reactions in this. So I want to find the reactions at A, the reactions at B, and in this rope. Okay, so here's what we have happening. Okay, so we've got our plate, of 981 newtons. Okay, I have a roller at A, a three-dimensional roller at A. I have a ball and socket at B, and then I have a cable that is perfectly vertical at C. Okay. In addition to that, I have a vertical force 300 newtons that is 1.5 meters back, okay, from the corner, and then I have an applied moment that's wrapped around that back edge in the amount of 200 newton meters in that back direction. Okay, and so that's what we have. The dimensions of the plate are 2 meters from A to B and 3 meters from B to C. It's a rectangular plate, and that will get us going. All right, so the first thing that we do is we draw a free body diagram, and to do that we need to set up a coordinate system. Okay, so for lack of any better one that's given, most problems in a textbook, they will give you the coordinate system. On a test, you might not get it. So you set it up. This follows our right-hand rule. Again, you know, if we do right-hand rule, put our thumb in the X direction, our forefinger in the Y. Try to kind of get my hand turned around here like that. Right? That didn't work very well. Anyway, the Z would be up. So that's the right-hand rule for X, Y, horizontal, and Z in the vertical. Okay, we go down our Y's. So again, we're playing the Y's game. Y's. Weight, we do have weight this time. That's the mass at 981 newtons. And we're going to assume that the plate is uniformly distributed. The weight is not heavier on one side than on the other. So the net resultant of all of the weight of this plate is going to be acting at the very, very middle of the plate. So it's going to be 1 meter from A, 1 meter from B, and 1.5 from B in this direction. And that gets me the center of the plate where that mass is acting. Okay. A is a roller. And so we know that a roller is a singular force that's perpendicular to the slope. So if we assume that the slope of the surface is horizontal, then my reaction is a vertical reaction acting up at A. Okay, and so that's an AZ because it's parallel to Z. Again, we've assumed that it's a flat surface that it's rolling on. Okay, if it wasn't, if it was on an incline or on a ramp, then of course, as you saw in the last couple of videos where we talked about rollers on inclines, this guy would turn and be perpendicular to whatever that support is. So you would have to define that plane and get the normal and all that. Okay, again, kind of getting a little sidetracked there. Okay, B is a ball and socket. We know that's all three forces, no moments. So I put a BX and a BY and a BZ. I drew them positive to the X, Y, and Z. Because we're doing this with scalars, what we assume for positive and negatives does matter. Vectors, it will take care of itself. But for scalars, we've got to put them on. So I'm putting everything in positive that I know. Okay, the cable, I can cut the cable. Okay, and I know that that's a tension in the rope, and the tension is pulling on the object that it's connected to. So if I draw my rope here like that, then this tension force is pulling on the top of that rope. Okay, all right, the other, so that's my support reactions. We do have, and that TC is in an internal because I cut the rope. Okay, and then so internal support reactions we've done. External, the external then is 300 newtons applied at that point here on the back wall, 1.5 meters up. So I've got kind of a line. It's on the same line as the 981. All right, so there we go. So now all we have to do is we've got a valid free body diagram. Ask yourself, what is the next step? What is always the next step? Write the equations. Okay, so we're going to do this with scalars. And so you'll notice I'm going to do sum of forces x. I'm not doing vectors. You could do vectors. It would probably be easier. You wouldn't have to be as careful, but I'm going to do it with scalars just to demonstrate how you could do it. So again, we've defined the coordinate system as these are all the positive axes here. All right, so I'm going to assume some forces for all of the forces acting in the x direction, which is positive down and to the left. Okay, and then so all that, if it's an equilibrium, sum of forces x equal to 0, and I go and I find anything on this picture that is acting in the x direction, and the only one that's there is bx. Okay, so bx is a 0 value because there's nothing else in that x direction. Rather uninteresting, honestly. Okay, by in this, we do the same thing. I'm going to do some forces in the y direction equal to 0. Now I'm going to go in the positive y direction, so kind of down and to the right on the paper. You can see this arrow matches that direction. All right, and the only thing in the x direct or in the y direction that we have on there is by, so by is also 0. Okay, so that's so 2 of them done, but we've used 2 of our equations. Remember, we only have 6 equations total. I've got the 3 forces and the 3 moments that we'll do on the next page. All right. So now if I look at this, I have I'm going to do sum of forces in the z, again assuming upward positive, all equal to 0. And anything in the z direction now shows up, and there's quite a bit this time. AZ is in there, it's acting up, so positive. BZ is in there, it's acting up, positive. 300 is acting down, negative, so that's that one. 981 acting down, negative. And then TC acting up, unknown, is positive. So I would write the equation as AZ plus BZ plus TC minus 300 minus 981 all equal to 0. Okay, and we're going to call that as equation 1 because I can't do anything more with it. There's too many unknowns. All right, so now we go in and we can start to look at writing some of the moment equations to help us solve this out. So I'm going to try to keep both of these on here. Let's go through and let's look at doing our moment equations. Okay, so if I do sum of moments about the x-axis, I can look at what do all these forces do as far as causing a moment about the x-axis. Okay, and so let's get my paper turned here a little bit so you can see. All right, so there's our picture. And so all we're going to do is we're looking for forces and perpendicular distance between the line of action of the force and the x-axis. So the first one we'll start off with is TC. Okay, he's acting up, and so his perpendicular distance to the x-axis is the distance from here to here on this rectangular plate. That's 2 meters. Okay, so TC times 2. Now, what we've got to be careful of is look at the direction. I've assumed positive being a moment vector that causes a positive moment about the x-axis. Again, we're kind of coming in and we're playing that game, right? Okay, and so this guy wants to wrap this thing around the x-axis that direction. It's a positive moment on there. So I would put a positive sign right there. Okay, we also get a moment from the 981, the self-weight. Okay, its distance is 1 meter, but this guy is now a negative moment because it's trying to go the opposite direction, right? It's pushing down and my thumb is now pointing negative x. So that's minus 981 times 1. Okay, I get a 300 times a 0, so I didn't even write that one because it's on the x-axis. AZ times 0 on the x-axis. I do get BZ times 2 positive because that would cause a moment. I don't know the value of BZ yet. Okay, BX doesn't cause a moment about X, and BY doesn't cause a moment about X because both of them are on this plane. It's a horizontal plane, and so the x-axis is in the same plane as BX and BY. Okay, because this line intersects the x-axis. If this plate had been inclined, these guys would contribute. Okay, so that's all we've done. So let's call that as equation 2 because again, I have two unknowns in my equation here, TC and a BZ on that one. Okay, all right, so that's my moment in the x. Let's go do sum of moments in the y equal to 0. Okay, so now we're looking to do the same thing, but now we're going about this y-axis here. Okay, first thing that we see on here is that I have a 200 Newton meter force about the y-axis. That is a negative moment because positive y is this way and he's pointed the opposite, so there's a minus 200 happening here. Okay, other things that will cause a moment, let's go with the 300. The 300 will cause a moment of 300 times 1.5, and that's going to cause us to want to rotate. If it's coming down, that's going to cause a positive. There's your positive y. So 300 times 1.5, that's a positive value. And then I get 981 times 1.5, positive value. I get AZ times 3, but he's going in the opposite direction, so that's a negative value. That's the AZ, and the BZ is the same thing, minus BZ times 3, also negative. And then, of course, we had the minus 200. So you can see it's it's tricky to do this with scalars because you got to make sure you get those directions right, especially on the moments. Sometimes it can be kind of hard to visualize. You got to get the positives and the negatives right, and we had a couple of negatives that snuck in on us here. All right, now you may be looking, well, what about the z-axis on this? Well, the only thing that would cause a moment about the z-axis, if I wrote the equation, and the reason I don't have it on this paper is let's do the moment about z equal to 0. We'll go upwards, positive here. Okay. AZ is parallel to z, doesn't cause a moment. 300 parallel, no moment. 981 parallel, no moment. TC parallel, no moment. A moment about a y-axis does not cause a moment about a z. Okay, and BZ parallel, no moment. So the only terms that would show up would be a BX and a BY. And this equation would be, if I did it, it would be BY times 3 meters, and that's a positive because he's trying to wrap this thing around the z-axis in a positive direction. Okay, minus BX times what would be 2 meters would be the equation like that, and all that equals to 0. Well, BX and BY we saw were both 0. So this equation doesn't get us anything else, okay? We're basically saying 0 is equal to 0. Well, that's true, okay, but it doesn't tell us a whole lot about that. So for this particular problem, that's why this equation wasn't originally written. I'll put it on there just so you have it, but that's why we have it and why we're not too worried about it. All right, so all we're going to do then is we're going to take what we called as equation. So these two equations, we call this one as 2. We call this one as 3, and then we had equation 1 back on the first page. If I solve all of this simultaneously doing algebra on this, you would find out that AZ is 790 newtons positive. BZ is 217 newtons, and it would be a negative, so it's acting down. And TC is 707 newtons tension. Okay? And so those are all different ways to do it. Now, there are alternative ways that you could tackle this problem, right? We took and did kind of a sum of the moments about the axes in general. You could also just choose a point in sum of the moments. So we could take and play the game that, go to the place with the most unknowns, okay? And clearly that's at B. So if I sum moments at B, we could figure out moments about the x-axis through B, the moments about the y-axis through B, and you would get an equation that looks something like this. I would get 981 times 1, because 981, so if I do it about the x-axis, let me apply that up there a little bit, just to kind of illustrate. Moment about the bx, again, we're assuming positive in the directions, so positive towards positive x on there. So I get 981 times b, and so this guy, if I'm looking for an x-axis through b, he would cause a positive moment relative to an x-axis through b. So that's a 981 times 1 positive. And then I get 300 from b is 300 times 2, again positive, because he's trying to rotate this thing that direction around an axis that is now situated here. Okay, obviously bx, bz, by, and tc do not cause a moment because they're all on that axis. So that's a good point about choosing b for this problem. So that gets us there, okay? And then I get an az that is going to be az times 2, and that would be a negative on that one. And then all of that equals to 0. And by choosing that point, before we had to solve 3 equations simultaneously to get the values, I could pick off az straight away, and you would find out that he is 790 newtons, all by choosing the point that you chose. Okay, so that's kind of one of the tricks and one of the advantages of taking on some free body diagrams, summing at a place where you have a lot of unknowns, and sometimes you get lucky and you can knock out most, if not all of them, and be able to singularly solve for az. Okay, and then once I have az, then I could jump back up into this equation and get bz, and so forth and so on. Okay, I could get the tension by doing the moments about the y-axis through B. Okay, so my y-axis is here. Okay, so my y-axis through B would be acting there. Okay, and so AZ doesn't contribute. None of the B stuff contributes. I would get 300 times 1 is a negative, 300 times 1.5 negative, 981 times 1.5 negative, and TC times 3 positive, all about that axis. Again, we're looking for an axis that comes through here. Okay, and that would be the equation that I just wrote here. However, you do also get the applied moment, so don't forget him sitting here back in the back. He only shows up in the moments about the y, and so it would be a minus 200 for that because of his free vector status. And again, you would have everything here except for TC. You could solve for TC 707 positive. It's a tension value, which is exactly what we saw the other way. So you can do these multiple ways. And then I could take and substitute this one into my original equation 1 to get BZ. So there's lots of ways to tackle these problems as we start to kind of look at it. All right, so that's kind of where we're headed with all of this. Okay, all right, so let's try another one, and this time let's see if we can do it with some of the vector stuff that we've learned about. Put it all to work. Okay, all right, so what I have is I have kind of a flagpole or a post that has a ball and socket at the bottom, and it has 2 cables pulling on the top of the post, the kind of stabilizer cables or something. Okay, and so I'm calling the bottom of the post as A, the top of the post is B. It is 6 meters up. Okay, and the cable goes from B to tied to the ground on the x-axis at point C at a position of 600. Okay, and then it has another cable B that is tied to a point D that is located at minus 360. So it's not on the y-axis. It's actually back a little bit, back in that negative x quadrant on there. And then at the top, I have a force in the y direction that is 1 kilonewton acting to the left or in the negative y direction. All right. Okay, so what we want to find then is what are the reactions at A? Okay, and so this is the way that we'll start to do that. Okay, so things that we know and things that we can write. Okay, if you remember, these are all the skills that we've learned back when we were dealing with vectors. Okay, the first one is that I would go through and I do a free body diagram. And if I did the free body diagram of the whole thing, it gets a little bit ugly. In fact, let me do that one just so you see why we've skipped it a little bit. Get my straight edge here. Sorry about that. Okay, so the first picture that we should always draw is the one of the uncut system. Now, again, I've kind of skipped that step because what you have is you have a force vector at A. I have what we were calling as my F vector happening here. and then you had cables coming down to a pin support at C. So that, now cables, their connection is always considered as a ball and socket. There is no moment. You can't bend a rope. Okay, it's only tension allowed. So there would be a force vector at C there. Okay, and then you get the other one that comes back over and does this. That would be my force vector at D there. Okay, and so if you go through and you look at this, how many unknowns do we currently have? Well, I've got a vector here, you know, and this guy is an FCX vector plus an FCY vector plus an FZ vector or CZ vector here, and this guy is an FDX vector plus an FDY vector plus an FDZ vector on that one. Okay, F we know, so we got that one. Okay, and oh, well, this guy is an FAX vector plus an FAY vector plus an FAZ vector. So the original system on this, if you look at it, and we take it back to its components, I know everything here, when you went and did this, that is going to be F vector plus, FA plus FC plus my FD vector on that, okay? And if you look, I've got 3 unknowns in this one, 3 unknowns in this one, 3 unknowns in this one, and even if I said this is all equal to 0, you would have 9 unknowns on this problem. All right, so one of the tricks that comes out of this, and one of the reasons I want to show this problem is anytime you have a cable, it's often better to cut the cable, and here's why. Okay, so keep that in mind. If I don't cut the cable, I get 3 unknown force vectors down at the reaction where it's tied to. And you could work through it eventually, probably. Actually, I think it's statically determined if you don't cut the cable, but yeah, it's not a real enjoyable time, not how I would want to spend my weekend, needless to say. So instead, what we're going to do is we're going to draw a free body diagram of the pole only, and we're going to cut the cables. Right, and if I do that, this free body diagram looks something like the following. So here's my AX, AY, AZ. That's that force reaction at A. I don't know those. That's what we want. Okay, and if I cut the cable, instead of getting 3 unknowns here, now I only get the 1 unknown that's the tension in the cable. And now here I get the 1 unknown that is the tension in that cable. And so I can trade 3 of these for 1 and 3 of these for 1, and now instead of having 9 unknowns, I would have 5. All right, and that's the advantage of what we're trying to do. So the free body diagram for that would look something kind of like this. Now, you do still have to create the vector for TC, but you can do that for tension, for tensions and cables. We've done this in a couple of examples in previous videos. Okay, using the position vectors to create a unit vector to create a force vector. That whole process is what we're doing here. All right, so I've gone ahead and I've kind of saved us some of the trouble of that step because I just kind of want to show the equilibrium process and the trick of cutting this and making it a whole lot more manageable. So TC is going to be 0.707 times the tension TC in the I direction minus 0.707 TC times magnitude tension in the K direction. That's the value of this vector. And you can see it's a 45-degree angle, right? It's 6 out and 6 up. That's 45 in that plane. That's where the 0.707 is coming from. Okay, cosine of 45. Okay, TBD or TD is a little bit more involved. You would have to do the tension TD multiplied by a position vector from B to D over the magnitude of B to D. So again, what is this guy? This is a unit vector that tells me BD's direction. Okay, and we're going to multiply that by the TD magnitude. And well, yeah, that's our vector formula, right? Being able to create that. Okay, and so if I go through the math again, RBD you can find, this RBD you can find, TD is unknown. So we can set this so that the TD vector is minus 0.333 TDI plus 0.667 TDJ and minus 0.667 TD in the K direction on those. Again, I don't know TD, so I have to carry it through. Just like I didn't know TC, it has to be in the equation. Okay, and it shows up in a lot of terms, but it's only one unknown in all of those equations. All right, so let's wrap this thing up then. So if that's my picture that we're looking to do, the next step is no different. So we've got our free body diagram that we're choosing to work with. Now let's go find the resultants of the forces. So here's my R, and there's my sum of forces. And so on this picture, what do we have force-wise? I have my force reaction at A, that's AX plus AY plus AZ, the force that's applied, oops, get that down a little bit, here. So there's my force that's applied, and then I have my tension in C and my tension in D. That's the equation. And all I'm going to do is I'm going to substitute all of those parts that we found into this. One other one I wanted to show you is that the force at the top of the bar, this F, was 1,000 kilonewtons acting in negative Y. So him as a vector is minus 1,000 J. And again, that would be kilonewtons on that. All right. So that's the other vector that you need. So we've got everything in vector form. Now we can go through and solve it with vectors. And we'll play the exact same game that we did in our three-dimensional equilibrium exercise. All right. So equation 1 then, I'm going to sum all of this stuff. And if I write all the parts, again, you got to be careful. The algebra gets long. This is what makes these problems really ugly. Okay, is that they're long and very prone to sign errors if you're not careful. But I think I've done this right, I hope. Okay, so all of the I stuff goes here. So anything with an I that came out of these four terms gets thrown in. So AX plus 0.707 TC minus 0.333 TD, all that's times the I. That's the X component. So all of that is sum of forces in the X equal to 0. That's one equation. Okay, do the same thing for the Y. It's minus 1,000 plus AY plus 0.667 TD. Okay, and all that's times J, and that's the sum of forces in the Y part of it. So remember, these simple scalar formulas all came out of the original vector equations. Okay, and then we can do the same thing for Z. Now it's AZ minus 0.707 TC minus 0.667 TD times K, all equal to 0. And you can see that that would give me a lot of information, but I can't solve any of them because they all have two unknowns. Okay, so now let's go through, and so we've got to find something to be able to unlock the rest of this. And it's looking like what we're going to need is the tensions in the cables to do it. So if we go back and we look at our picture and we write our moment equation here on this, what do we have? I have two unknowns, TC and TD here. I have three unknowns in A down here. Okay, and of course I know the F. So this seems like the logical point to some moments, because when I do that, these guys will not show up in the equation. All right, that I would get RBA, crossed in into, F vector plus TC vector plus TD vector. Now you're looking at that you might not recognize this form, but if I do this, and we write this out just a little bit more, if I wrote the whole thing, which was probably what I should have done in the notes, so I'll put it here. If I do sum of the moments, and we're going to go about the A moment vector, all equal to 0. Okay, what do we get? We get R from A to A crossed into AX, R from A to A crossed into AY as a vector, vector. What's your vector, Victor? Ever see the movie Airplane? All right, R from A to A crossed into an AZ vector. That gets me that piece. So those are three of them. Okay, then I get also the moments that these other three guys cause. And so that's going to be an R from A to, what would be R from A to B vector crossed into my tension in C. Okay, and then an R from A to B crossed into a tension D. Okay, and then an R from A to B crossed into my F vector. Okay, so it's a pretty long equation on all this, but all of this is equal to 0. All right, now by choosing A, this term, and this term all vanish because R from A to A is 0. Okay, all right, so what we're left with then is the pieces that are here. So it's RAB crossed into T, RAB crossed into TD, RAB crossed into F. Okay, and so all I did was they all have a common value, okay? And so basically, in effect, what you can do, since they're all at the same point, we could turn this into, here's my pole, some force resultant at that point, which is just the resultant of these three guys. So F plus TC plus TD would be this guy. And then I would have my three unknowns down here. And now it's just one cross product. So by writing it this way, you had to do, by writing it here, there was three cross products required. But if I combine those, because they all meet at a common point, I can turn that into one single resultant, where this guy is TC plus TD plus my f. Okay, so that's all I've done is I've done a little bit of vector algebra to simplify this thing quite a bit. But if I take this equation, set it equal to 0, and then simplify it, that's what we were getting here. Okay, because again, this is what we were calling kind of as that FR resultant on the top of the pole. Okay? All right, so then the only thing that I need is RBA. Well, that's easy enough. Right, we can come back to our picture and R from, and that should not be BA, it should be AB. Okay, and then that should be, let me clear that out, R vector from A to B. Okay, from A to B. I want the vector from A to B as we had drawn down here. That's the vector that I need. Again, my label, I just noticed I labeled that guy completely backwards, R from A to B. Okay, and so that is clearly going to be a positive 6 in the Z direction, so it's going to be a 6K vector, and that's what we've got here. Okay, and then I plug in all of what I have for F, TC, and TD. That's this huge line here. Okay, and then if I do the cross product on this and kind of collect the I terms and simplify it, okay, I'm going to wave my magic wand and save us the pain of the algebra. This is where it gets ugly on this. But at the end of the day, what I get is I get a 4TD plus 6,000 is minus 4TD plus 6,000 times I. That's the MX moment. I get a 4.24 TC minus 2TD plus MY times J. And then I get nothing for a moment about the Z because that point is on the Z axis. So there's a 0 on this guy. All right. And so with this, now I can say, well, I know that I have to have sum of moments X equal to 0. Okay. And IJ's. Wow. Let's try that again too. Got all my subscripts messed up today. So that's MY. This is sum of M at X. Take that. We are saying that that's equal to 0, and we're saying that that's equal to 0. Okay, and so what we have then is it's basically this term has to be equal to 0, and this term has to be equal to 0, and this term is already 0. And I basically solve these independently. Well, now I can pull off TD out of this one. TD is 1,500 newtons tension. Got it. Okay, and then I can take TD and go into this one, which is 4.24 TC minus 2 TD. Plug in your TD value here, and you get TC is 707. Okay, newtons in tension, in the tension in the cables. And again, this is the magnitude of the tension. We still have all those coefficients that give you the direction, the 0.667 and whatnot to make the vectors. But with these, I am now armed with the ability to go back up into here, into our equation 1, substitute those back into equation 1, and you'll find out that AX is 0, AY is 0, and AZ is 1,500 newtons. AX is 0, AY is 0, and AZ is 1,500 newtons acting upward. And that's the basis for these for how you would handle a three-dimensional problem. So I hope that's made sense to you. I know it's a little, they're long problems. Obviously, this is a longer video, and we only worked 2 problems. Equilibrium problems, by their nature, are very, very long. It's one of the reasons we like to get computer programs that can do structural analysis, is we don't want to do all this by hand because you're prone to errors, sign errors and labeling errors. I've demonstrated quite eloquently both of those in this lesson, but but it is doable if you're careful. So just keep after it. The more problems that you work, the better off you'll be. For my students, I'm telling you now, chapter 4, the problems are the longest of the entire semester. Okay, just because it's so many unknowns and a lot of algebra, and problems take multiple pages to solve. It's just kind of the nature of it. So I hope it's made sense to you. Again, I apologize for the inconsistency in the labeling there. We'll fix that going forward. I hope it's made sense to you. As always, if you've got any questions, leave us some comments down below, and we'll get back to you and try to help you out in any way that we can. Otherwise, toss us a like on the video, please, and subscribe to the channel, and we will see you all next time. Happy engineering.